Hello and welcome. In this video, we explore the extreme world of engine friction and how a breakthrough in nano additives is changing the automotive industry. Inside a modern internal combustion engine, conditions are essentially a controlled inferno. Every single minute, thousands of explosions propel the pistons, generating localized temperatures that can easily exceed several hundred degrees Celsius, alongside contact pressures high enough to crush solid steel. In this harsh mechanical environment, a microscopic, paper-thin film of motor oil is the only thing standing between smooth operation and catastrophic metal-on-metal destruction. Ideally, motor oil creates what engineers call a hydrodynamic film, a liquid cushion that keeps rapidly moving metal parts completely separated. But the reality is far from ideal. During extreme acceleration, heavy towing, high RPMs, or even idling in traffic, this protective liquid layer becomes perilously thin. When this happens, the engine enters a harsh state known as boundary friction. Under a microscope, machined metal isn't perfectly smooth. It looks like a jagged mountain range. During boundary friction, these microscopic peaks actually collide and tear into each other. Overcoming this friction remains the ultimate challenge in modern engineering. Today, up to 20% of the energy generated by fuel is wasted, lost entirely to mechanical drag. To combat these extreme conditions, raw base oil alone is simply not enough. Modern motor oil is actually a highly engineered chemical cocktail. In fact, up to 20 to 30% of the oil you pour into your engine consists of specialized additive packages, each performing a vital function. These packages include detergents and dispersants, which act like microscopic soap to wash away soot and prevent sludge buildup. Viscosity index improvers are added to ensure the oil remains fluid in freezing winters, but stays thick enough in the blistering summer heat. Meanwhile, antioxidants protect the fluid itself from chemically breaking down under severe thermal stress. However, when the liquid hydrodynamic film breaks down and the engine faces boundary friction, survival relies entirely on a specific class of additives: anti-wear agents and friction modifiers. For decades, traditional anti-friction additives have been the industry standard. Chemical compounds like ZDDP create sacrificial layers, while solid lubricants like graphite or molybdenum disulfide operate on the principle of sliding flat layers against each other. But under modern engine loads and high temperatures, these conventional additives reach their limits. Chemical films deplete over time, and solid layers can deform. Non-uniform particles may even cause abrasive wear rather than prevent it. To create the next generation of friction-modifying additives, the nanotechnology industry turned to advanced forms of carbon. But as tribologists quickly discovered, in the brutal environment of an engine, the geometric shape of the carbon additive changes absolutely everything. Let's look at the alternatives. First, there is carbon black. While cheap and commonly used, its molecular structure is amorphous and irregular. It lacks the perfect crystalline architecture needed to reduce friction. Under extreme pressure, its jagged particles often act more like microscopic soot or a mild abrasive impurity rather than a high-tech lubricant additive. Next, scientists tried graphene sheets, flat, two-dimensional layers of carbon. While incredibly slippery in theory, flat graphene faces a fatal physical flaw when suspended as an additive in liquid motor oil. Driven by molecular attraction, these flat sheets naturally want to clump together and restack, much like wet sheets of paper sticking to one another. Under the immense shear pressure of moving pistons, these sheets easily fold, shear, and crumple, losing their nanoscopic advantages. Then came carbon nanotubes. Imagine them as microscopic, ultra-strong strands of spaghetti. While durable, their long, one-dimensional shape causes them to tangle and intertwine into messy bundles. This makes it notoriously difficult to keep nanotube additives evenly dispersed in a base oil. When they tangle, they alter the oil's viscosity and create a severe risk of clogging fine engine oil filters. In response to the physical limitations of amorphous soot, flat sheets, and tangled tubes, materials science introduced a breakthrough class of anti-friction additive, carbon nano-onions, or CNO, also known as onion-like graphene. Today, nanotech innovators like Pyrogen are pioneering the synthesis of this material, specifically for use as a high-performance additive for motor oils. From a physical perspective, this additive is a unique three-dimensional form of carbon with a flawless, spherical, multi-layered architecture. Picture a nanoscale matryoshka doll or an onion, where 40 to 60 graphene layers are perfectly nested within one another. At just 30 to 60 nanometers in size, these structures serve as an ideal additive because they easily penetrate the tightest clearances inside an engine. With an atomic structure identically matching ideal graphite, this closed spherical form ensures exceptional purity. Unlike flat sheets that crumple or tubes that tangle, the flawless spherical shape makes CNO additives incredibly resistant to external stress. The fundamental difference between onion-like graphene and all other carbon friction modifiers is how it behaves in motion. Once blended into the motor oil, billions of these nanospheres act as perfect nano-bearings. Instead of merely sliding, this additive introduces rolling friction modes. They physically separate the rubbing metal surfaces, acting like microscopic ball bearings that never lose their perfect shape, even under colossal cyclic loads of up to 5 gigapascals. This structural integrity makes this additive especially crucial during a cold start. Automotive engineers know that up to 75% of all engine wear occurs in the first few seconds after ignition. When a car sits overnight, gravity pulls the oil down into the pan. But because of their microscopic size, carbon nano-onions permanently embed themselves deep into the natural micropores of the metal surfaces. Even when the liquid carrier oil drains away, billions of nano-bearings remain locked in place, providing instant rolling protection before the oil pump even wakes up. Integrating onion-like graphene into lubrication systems as an advanced additive provides measurable results. It can reduce the friction coefficient by up to 80%, translating to fuel savings ranging from 5% to 10%. Engine wear drops significantly, drastically extending the lifespan of critical components. Furthermore, possessing record-breaking thermal conductivity, this graphene additive instantly dissipates excess heat from highly loaded surfaces, protecting the base oil from thermal stress. For the lubricant formulation industry, the material's processability is a true game-changer. Because they are perfectly spherical and lack long fibers or flat edges, CNO additives engineered by Pyrogen distribute evenly across a wide range of base oils. They do not agglomerate, tangle, or settle. Crucially, they blend harmoniously alongside other existing additives, like detergents and dispersants, ensuring highly stable, flawless performance throughout the oil's lifespan. Ultimately, the evolution of motor oil is a continuous battle against friction. By integrating advanced nanomaterials like onion-like graphene into modern additive packages, standard motor oil is transformed from a passive liquid cushion into an active, intelligent protection system. It proves that the future of automotive reliability lies in atomic engineering, managing heat, protecting metal, and making every movement more efficient. Thank you for your attention. Follow me.